okay, this function is Cauchy integral. We did that in class. It turned out to be yes. The rationals have Lebesgue measure 0. We did that in class. What was that? True or false? I surround each rational. I enumerate the rationals. I surround one. I surround the nth rational, r sub n, with an interval of length epsilon to the n. Then I have a geometric series of epsilons, right? First term is epsilon, constant ratio is epsilon, so it sums to epsilon over 1 minus epsilon, and the limit as epsilon goes to 0, it goes to epsilon, which is arbitrary, hence the measure, the total amount of length that I need to capture all the rational numbers. So that is true. The Cantor middle third set has measure 0. We took away the total measure of the middle thirds and discovered, since it's a third, right? 1/3, 2/9. How did it go after that? 4/27 or whatever. We did that. We had a geometric series that turned out to be 1. So if you're taking total measure 1 out of the unit interval, what is left? The measure of the Cantor set would be 0. The next one you haven't heard of. One after that. The Cantor middle third set is uncountable. Yeah, it consists of all ternary decimals that avoid 1s. And so all the decimals will use either 0s or 2s, ternary decimals and 0s or 2s. They're uncountable. Can you see why they're uncountable? Suppose they work. Then you make a list.
Yeah.
And then you use the diagonalization process to create a new one that differs from the nth one on your list and the nth place. And so you can never be confident. You can never get a complete list. If you can't get a complete list after you said, I had a complete list, well, that's the contradiction. So they would have to look up Cantor diagonalizations. You probably do this in high school. Yeah, you prove that, that was a very standard. You prove in high school that the reals are uncountable. The reals between 0 and 1. You write them as decimals, and you say, oh, assume they are. You list them. And then you say, pick a digit that's different from the first one in the first place, second in the second place, third in the third place, and so forth. You can certainly pick a decimal that does all that. And then you ask, okay, I have this decimal. Where is it on the list? It's nowhere because it always differs from anything that's already on the list, which means you didn't have a list. It was complete. You had a list. It just wasn't all of them.
And then you can do it again.
Oh, yeah. Well, right. Sure. And you can do that with decimals that consist of just 2 digits. You can show the binary decimals are uncountable. You can show that ternary decimals that use no 1s or no 2s or no 0s, as long as you have the 2 things so that you can be different, you can show that they're all uncountable. Oh. So the Cantor middle third set is uncountable. And it has the weird property that it doesn't contain any intervals, any complete intervals, because you're always taking the middle third out of something. It's just a bunch of leftover stuff. But a lot. It's uncountable. Smith-Volterra Cantor sets have positive measure. I was going to try to explain that a little more fully. SVC sets are called fat Cantor sets. And what they are instead of middle third sets, they're middle fourth, middle fifth, middle sixth, middle seventh, etc. So if you take away less each time, unlike the middle third set, which just coincidentally takes all the measure away, you're left with something. But the Smith-Volterra Cantor sets have that same strange property. There's no interval contained in them, and yet they have positive measure. I cannot get my head around that. There's some length there, but you can't put an interval in. That just seems too weird. Well, that's the way these things are. anything like that that's been.
So that's true.
Yeah, they have positive measure. He makes kind of an oblique reference to that in here that you, it's possible to have sets. You know, once you have that, you have a set that has positive measure. You can make some funny things happen when you try to do it. The middle third set is weird enough. We'll get to proving that there exists a function called the devil's staircase that goes from it's defined from 0 to 1, and its range is from 0 to 1. And it only moves on the Cantor set. On the complement of the Cantor set, it's constant. So the derivative is 0 on the complement of the Cantor set, which means the derivative is 0 on a set of measure 1. And it only moves on the Cantor set, which has a set of measure 0. So it's a classic example where the fundamental theorem of calculus fails. F prime is 0 almost everywhere. So you would think that when you integrate that, you get 0. But you don't, because the difference at the ends of the function are 1 and 0. It's weird. We'll go through that when we talk about the Omega. A fundamental theorem of calculus asserts the existence of a definite integral in an evaluation. I think that's true. I've chosen, just for clarity, to split out from the fundamental theorems these theorems that have to do with recovery of functions from the recovery of a function from a derivative and the recovery of a function from its integral. As part of the fundamental theorem of calculus Cauchy style, if you say that f prime is continuous, then you can recover the function capital F from capital F prime via the integral. The flip side of that is to start out and recover the function from its integral. You know, go find the integrand function if you know what the integral already is. I've left that out. I will add that to the little note that I put on the now. I just haven't finished it. I haven't elevated it to the status of the fundamental theory yet. It's just a recovery theory. Okay. A uniformly convergent sequence of functions is continuous. True or false? False. How can I change that to make it true?
The uniformly convergent sequence of continuous functions.
If I put continuous there, that is true. If there's no continuous, it's false. If it's pointwise convergent instead of uniformly, it's true. Not true there either. So the magic word uniform and the magic word continuous have to be there to activate that theorem. Stirling's formula is an exact formula for the factor function. I don't think so. It's an approximation. Which in the limit is asymptotically exact. That ain't exact, right? Asymptotically exact just means as n goes to infinity, the ratio of n factorial to the Stirling expression is 2. So the relative error goes to 0. But it's still not exact. Wallace's formula can be used to evaluate the undetermined constant with the Wallace-Stirling formula. That's exactly what we did there. Right? The area of a parabolic segment was first determined by Hippocrates. I just had to say that. I just had to say that. Every time I think of that kid in the 9th grade. No. Hippocrates with the area of the loop.
He was looting.
Looting. The two great results of Greek geometry are generally considered to be the theorem about the area of a parabolic segment and the determination of the volume of the sphere, both by Archimedes. Yeah, Aristotle